Warm greetings, friends, and my dear students. Today I am going to give a lecture on the torsion of shafts. The shafts may be of solid circular section or hollow circular section, but compared to the solid circular section, hollow circular section of the shaft is more economical because we are going to save the material, the corresponding value of the torque and the speed of the shaft and the angular twist. So before that, what is called as a twisting moment or the torque. So twisting moment or the torque is nothing but the force into the perpendicular distance where the force is applied. For example, you can take the bicycle as an example where we are applying the force on the pedal, and this force is converted by means of torque by means of a lever arm. So the force into the lever arm length, in the case of bicycle, is produced by the torque. The unit of torque is the same of the couple, that is kilonewton meter or newton millimeter, or you can call it as newton into meter. If you consider a shaft of length L, it is subject to a solid circular shaft of diameter small d, and the length of the span of the shaft is L. So what will be the angular twist or the shear stress or at any radius from the center of the shaft or the maximum radius, that is the outer surface of the shaft. So here capital T is equal to the applied torque in Newton meter, then J is equal to polar moment of inertia in meter to the power 4, and capital C is equal to the shear modulus of the shaft, and J is equal to the polar moment of inertia in meter to the power 4 or millimeter to the power 4. And theta is the angular twist, which will be always measured in radians. Even if it is given in degree, you have to convert as radians. So 1 degree is equal to pi by 180 radian. So T by J is equal to C theta by L is equal to Fs by R, where Fs is the shear stress at any fiber from the center of the shaft, and R is the radius from center to the outer surface. At any point you can able to find the shear stress, but the maximum shear stress when small r is equal to capital R, you will get the maximum shear stress, that is the outer surface of the shaft. At the center the shear stress will be 0, and you know that moment of inertia for a solid circular shaft about x-axis and y-axis is equal to pi d per 4 by 64. Ix is equal to Iy because of symmetrical section of the shaft. So if you are putting in the polar moment of inertia, J or Ip is equal to pi into d power 4 by 64 plus pi into d power 4 by 64. So if you are simplifying it, you will get pi into d power 4 by 32, where small d is the diameter of the shaft, either in millimeter or meter. So you will get the polar moment of inertia in terms of millimeter to the power 4 or meter to the power 4. So we can get the corresponding value of shear stress at any radius of the shaft section from the center by substituting the corresponding value in the torsional equation. T by J is equal to Fs by R. So where J is the polar moment of inertia, pi into d power 4 by 32. If you are substituted, you will get a maximum shear stress Fs is equal to T by J into capital R, where capital R is the outer radius of the shaft. That is when small r is equal to capital R, that is D by 2. So in that way you can calculate the maximum shear stress. And how to calculate the angular twist in radians? You take the equation of T by J is equal to C theta by L. You know that the product of C theta is equal to the torsional rigidity of the shaft. We have seen EI is equal to the fluxural rigidity of the beam in the case of beam. Similarly, the torsional rigidity is equal to C into J, the product of the shear modulus of the shaft into the polar moment of inertia. So theta will be the angular twist in radian, that is equal to T by J into L divided by capital C, where capital C is equal to the shear modulus of the shaft section, whether it is a solid circular shaft or a hollow circular shaft. And what will be the power transmitted by the shaft? Power transmitted by the shaft is denoted by capital P, that is equal to 2 pi n T divided by 60,000 in kilowatts. It is an empirical formula, where P is the power transmitted by the shaft in kilowatts, N is the capital N is the speed of the shaft in RPM. Even if it is given revolution per second, you have to convert into RPM, that is revolution per minute. And T is the torque applied in the shaft, either it is a hollow shaft or the solid circular shaft. So in that way you can able to calculate the corresponding value of the angular twist. So like that, whatever be the known value of the data is given, we can find the other quantity. So like T or J or the Fs or angular twist or even the length of shaft also can able to calculate. As that of the section modulus of the beam, here polar modulus of the shaft section. The polar modulus of the shaft is denoted by capital Z suffix P. So it is nothing but the ratio of the polar moment of inertia to the maximum radius of the shaft. It is when small r is equal to capital R. So therefore, for a solid circular shaft, the polar modulus ZP is equal to pi d per 4 by 32 divided by d by 2. So what will happen? So pi d cube by 16 in terms of millimeter cube or meter cube. So that is the value of the polar modulus, pi d cube by 16 in millimeter cube or meter cube. So this is how we can find the polar modulus of the solid shaft as well as the hollow shaft. Thank you very much for patient listening. Goodbye. வாழ்க வையகம், வாழ்க வளமுடன்.